Welcome to the channel Physics by IITians, where we learn physics, understand physics to crack any examinations and related interviews. Last time I discussed about dispersion phenomena. So from dispersion, we all understand that why we get bigger pattern whenever white light is incident on a prism. So I hope you all can understand that from the dispersion phenomena, that whenever the photon particles or the electromagnetic waves of the light is incident on the medium, that is the dispersive medium like prism, it can induce vibration, and we can get dipole moments out of that vibration, the force vibration of that electrons, and we get the permittivity is frequency dependent, and the refractive index is frequency dependent. So the refractive index decide the velocity of the particular wave. So due to the frequency dependency of the wave, or refractive index, there will be different velocities for the different wavelengths. So as white light is not a monochromatic light, so the different components of the white lights from violet to red will have different velocities inside the prism. Thus they will we will get the dispersion phenomena, that is Vibgyor pattern. So today we are very familiar with the two name, that is phase velocity and group velocity. So do you understand what is phase velocity, what is group velocity? Can you visualize the thing? Why do we need this? Why do we need these two terms, that is phase velocity, group velocity, whenever we are referring a wave, or rather not a wave, it should be a wave train. Now we understand it physically, and I also discuss what will be the effect of the phase velocity or group velocity whenever the wave train is passing through a dispersive medium or through a non-dispersive medium. What will be the consequences? And I will discuss the previous year questions. So let's start, friends. So before starting, I want to show you a photo of a diagram of a wave packet. So this is a wave packet. Why is it looking like this? Okay, do you understand that in case of wave packet, there is not one wave, rather it is the superpositions of superposition of infinite number of waves, and differing only smaller frequencies or smaller wavelengths. That's why the wave packets are taking this shape. How do you get this shape? From mathematically, you can get this shape from Fourier transformation. Please do this by yourself. You take the infinite number of waves and superpose it, and you get the shape of the wave train. And whenever the meaning of this, that whenever there are infinite number of waves that are superposing, the wave train you will get, the diagram will be like a delta function. That's why we can denote particle as a matter wave, because it is composed of the infinite number of waves differing only smaller in frequency and smaller in wavelengths. Now, in case of wave packet, we are usually we hear the term, that is group velocity and phase velocity. Now, this is I want to show that this is the wave packet that is denoted by the blue line, and this is the envelope that is denoted by the dotted line. So why I am showing you that? Because the group velocity and phase velocity is directly related to the diagram. So now from the name, that is the phase velocity. Phase velocity, what do you understand? That is the velocity of the phase of the individual waves. That is the phase velocity of a monochromatic wave. If I want to write in terms of the monochromatic wave, the definition, the monochromatic wave, the phase velocity is the velocity with which a definite phase of the wave, that is its crest or its trough, is propagated in a medium. Okay, and can you measure experimentally? Can you measure phase velocity experimentally? No, it cannot be measured. Why? Because you have to distinguish between the successive waves for a monochromatic wave. So because they all are exactly similar, how is it possible to distinguish them and do the distinguish marking on the wave? So this is not possible, right? So that's why we do not cannot measure the phase velocities experimentally. Okay, now let's come to the group velocity. So before that, I have told you about the dispersion, so we should know about the dispersion medium. Okay, I will tell you the definition after some time. So let's come to group velocity. So from the name we all understand that the group is something that is, I mean, the velocity of a group. And what is the group here? Group is the group of the waves. I have already told you, in case of wave trains, they are consisting of several number of waves. So what will be their group velocity? So the group velocity of a wave is the velocity with which the overall envelope or shape of the waves amplitude propagates through the space. Okay, how can you understand it? Okay, let's back to the diagram. So here you are showing that these are the individual wave packets. So the individual waves inside these wave packets, they have different phases. They have different at any instant, they, some of them have crest, some of them have trough. So if you want to denote the individual waves phase, you have to denote it by phase velocity. But if you want to denote the envelope velocity, you will denote it by group velocity. Okay, so now understand it mathematically. How does it come, where does it come from? So it is denoted by Vg, that is group velocity, and phase velocity is denoted by Vp. Now let's take the simplest case. The simplest case is the superposition of two waves of slightly different frequencies, and they are producing the beats. So we are taking only the two wave superposition case. Now we want to understand that what is the relationship between the Vg and Vp, that is group velocity and phase velocity. So we consider the superposition of two waves of slightly different frequency, that is one is having nu 1, another is having nu 2, having the same amplitude A, and lambda 1 and lambda 2 are the wavelengths of the two waves. So we can write these two waves as y1 equals to a sin omega 1t minus k k1x, and y2 equals to a sin omega 2 t minus k2x. So it is propagating along x direction, and we are denoting the waves as y1 y2. So we are describing it along the y direction, these are the y1 y2, and along x direction this is the propagation. So look here, you are plotting the two waves with slightly different frequencies, and you are getting the resultant wave like this term. Now if the number of waves that are superposing is increasing, then slightly, then surely this hump that are forming, it will be narrower and narrower. And if there are infinite number of waves that are superposing, this hump will really like become a delta functions. So this delta functions, surely if we assume that how particles or matters can be realized as a wave, because matters can be realized or composed of, realized to be composed of infinite number of waves. So if there are infinite number of waves that are superposing with each other, we can get delta function out of there. So the delta function will denote the is. How can you get it? You can get this thing mathematically from Fourier transformation. So let's back to our discussion that we took the two different waves having two different frequencies, angular frequencies, and two different wavelengths. So we get two different omega 1 and omega 2, and different k1 and k2, where lambda 1 and lambda 2 are the different wavelengths. Okay, so and k1 k2 are the magnitude of propagation vectors of the two waves. What will be the resultant wave? So you need superposition, so you will add these two waves, and you get that a sin k1x omega 1t plus a sin k2x omega 2t. Now sin a plus sin b, you directly put the formula and you will get that 2 sin a plus b by 2 into cos a minus b by 2. So 2a cos, I am writing the cos term first, 2a cos k1 minus k2 by 2x minus omega 1 minus omega 2 by 2t into sin k1 plus k2 by 2x minus omega 1 plus omega 2 by 2t. So you have to understand that this resultant wave, actually this wave, which this is the wave that we are representing. Now we have to analyze the things that what we are getting. If k1 is nearly equals to k2, so we can denote it by k, and omega 1 is nearly equals to omega 2, we can denote it by omega. So what will happen these two things? I am telling you, this will give you the phase velocity and this will give you the group velocity, because this k1 minus k2, so the phase velocity Vp is omega by k, so k1 plus k2 by 2 will be roughly 2k by 2, that is kx, minus omega 1 plus omega 2 by 2, that will be omega 2 omega by 2 into t, that is omega t, that is kx minus omega t. So the wave is propagating along x direction with a velocity, individual waves with a velocity v, that is omega by k. Okay, and this is the group velocity, because these two terms, these are the differences between the two k, and the ratio between the two k, difference of the 2k and 2 omegas, that is the group velocity is d omega by dk, or you can write it as omega 1 minus omega 2 divided by k1 by k2, k1 minus k2. So this is the phase velocity, which denote the velocity of the carrier waves, and this is the group velocity, which denote the velocity of the envelope. Now this term, whenever this k1 is nearly equal to k2 and omega 1 is nearly equals to omega, this cosine term will be very small. Okay, now let us find out the general expression for the Vg, and how Vg and Vp are related to each other. And also we have understood that this Vg, that this expression is holding for general case of any number of superposition of waves. It is we have already only for done it for two number of waves, but it can be valid also for infinite number of monochromatic waves continuously with continuously varying frequency. So it is very much important. So what will be the relation between Vp and Vg, that is phase velocity and group velocity? So we know that Vp is omega by k, and if we take the derivative with respect to k, that is dVp by dk, we will get 1 by k d omega dk minus omega by k square. So you, after simplifying and write it d omega by dk as Vg and omega by k as Vp, we get Vg equals to Vp plus k into dVp by d lambda. Now look at this term. What is denoted by dVp by d lambda? Now we define the definition of the dispersive medium. So a dispersive medium is a medium in which waves of different frequencies travel at different velocities. With electromagnetic radiation such as the light or radio waves, dispersion corresponds to a frequency dependent variation in the index of refractive index of the medium. So due to the variation of the refractive index, we get different velocities at different wavelengths. That's why the dispersion is happening, and the corresponding medium is dispersive medium. So whenever there is variation of dV by d lambda, so this is the dispersion happening, that is variation of velocity with the variation of the wavelength. Now for light wave in vacuum, dVv by d lambda will be 0. There is no variation of velocity, or the ratio will be 0. So we get that Vg equals to Vp, and we all know this light wave, the vacuum, the speed of the light wave will be c, that is the speed of light. Now whenever Vp by v lambda, dVp by d lambda is positive, then Vg is greater than Vp, and dVp by d lambda is negative, then Vg is less than Vp. Okay, how do you understand? You have to understand that this omega is equals to proportional to k. So I will discuss it, okay, in the conclusion term. So what are the conclusions we get? That a wave train can be obtained by superposition of monochromatic waves of different wavelengths. It must be propagated with group velocities, not phase velocity. The energy carried out by this wave also transported with group velocity. All physically measurable quantities associated with the wave packet are also propagated with group velocity. What is phase velocity then? The phase velocity is the velocity of propagation of the phase of the disturbance, and in some cases the phase velocity can be greater than c, but Vg must be less than c. Okay, or maximum it can be c for the light. For matter wave, let us find out what will be the Vp and what will be the Vg. For matter wave, we all know that E equals to h cross omega, P equals to h cross k. We get it from quantum mechanics, and Vp equals to omega by k, that is E by P. Okay. Now for free particle, E equals to P square by twice m. So Vp will be E by P equals to P by twice m. So Vp is V by 2. If you think that this V is the particle velocity, so this should be Vg, that is group velocity. So the phase velocity is half of the particle velocity or its group velocity. Now for the relativistic case, that is V is nearly equals to C, what will happen? For the relativistic case, Vp equals to E by P, that is E will be mc square divided by m into V. So this will be c square by V. Now V equals to Vg, so Vp into Vg will be equals to c square. Now you just notice here that V is less than C, this term is less than C, so Vp phase velocity is greater than C. So this particle cannot be represented by such a wave, it should be represented by a wave packet. So the relativistic energy E equals to root over p square c square plus m naught square c to the power 4, from where we can calculate Vp, that is Vp equals to E by P, that is c into root over 1 plus m naught square c square by p square, or you can write it as equals c root over 1 plus m naught square c square by a square into lambda square. So if that Vp will be greater than c when lambda increases. How lambda increases, this Vp will be greater than the velocity of light c. But there is, don't afraid, don't worry, the nothing, no energy is propagating along Vp, or nor the wave is propagating along Vp. So neither the energy nor the wave, it is the disturbance of that particular phase, that is the speed, that is denoted by Vp. And what will be the Vg? Vg will be d omega by dk, that is dE by dP. After calculating we get Vg equals to dE by dP will be Pc square by E, that is its particle velocity. So group velocity is the particle's velocity. So in case of dispersive medium, if omega is directly proportional to k, then the group velocity is equals to the phase velocity, because omega equals to, this is the case, suppose omega equals to ck. What do you mean? That is omega by k equals to c, and this is exactly equal to the group velocity. And how do you denote it? You denote it by a straight line. And how to understand what is the group velocity, what is the phase velocity? You take the tangent over here. Suppose you take a particular point, you want to find out the group velocity, so d omega by dk, you have to take the tangent here. And also if you want to know the phase velocity, you need this theta angle. And here both the thetas, that is Vp omega by k and d omega by k, both are same, they are producing the same angle, so Vp equals to Vg. Now if omega is a linear function of k, that is omega equals to ak plus b, then the group velocity and phase velocity are different, and the envelope of the wave packet will travel at group velocity, while the individual peaks and troughs within the envelope will move at the phase velocity. If omega is not a linear function of k, what will happen? If omega is not a linear function of k, so there will be different frequencies for the in that that is inside the wave packet, or that are contained in the inside the wave packet, there are different frequencies, so there will be different group velocities. So although the envelope is moving with a particular single frequency, but the wave number components are moving with different velocities, so we get a distorted envelope. So suppose you are sending your signal in form of a square wave, what will happen? In form of a square wave, if you are sending your signal, it is passing through a dispersive medium, there will be spreading or distortion of the envelope of the wave. So what do you do to get rid of such kind of distortion in the signal? We actually, suppose this is our signal, the frequency of the signal is quite lower, and we modulate the signal, we give another carrier frequency of higher omega, and we modulate the signal, and after modulation means we are defining the frequency range with certain omega. Suppose this is omega prime and this is omega naught, so we are defining this, or we are limiting our frequency range within omega naught plus minus omega prime, so that there should be minimum distortion. Okay, so this is the very practical applications of the group velocity, phase velocities, why these are so important. Okay, in communication this is very important, whether it is dispersive medium, the group velocity will, what will happening with the group velocity, so that our signal should not be distorted, and what should we do to get rid of such kind of dispersion. Now let us focus on problems. So the first problem is the dispersion relation for a certain type of excitation is given by omega equals to a k to the power a, where a and small a is greater than 0. These are two constants. For this excitation, the group velocity is less than phase velocity when. So they ask you when Vg is less than Vp. So whenever there is Vg is less than Vp, that is omega equals to a into k to the power a. So Vp equals to omega by k, that is a k to the power a minus 1, and Vg equals to d omega by dk, that is a into small a into k to the power a minus 1. So to get Vg is less than Vc, we get Vg by Vc should be less than 1. So you put the two values for Vg and Vp, we get that a equals to a should be less than 1. That is our option C is correct. Next, this is the option C is correct. Now next, go to the next question. The question is the relation between angular frequency omega and the wave number k for a given type of wave is omega square equals to alpha k plus beta k cube. So this relation, that is omega k, is called as dispersion relation. Now can you understand that why is it calling the dispersion relation? Because this is giving you the phase velocity, this is giving you the group velocity, and these are the direct consequences of the dispersion phenomena. So this relation will decide you the whether the group velocity is higher, whether the phase velocity is higher, what will be the behavior of the group velocity, what will be the behavior of the phase velocity under the dispersion phenomena. So that's why this relation is called dispersion relation. So the in this question the dispersion relation is omega square equals to alpha k plus beta k cube. The wave number k naught for which the phase velocity equals to the group velocity, that is Vp, equals to Vg at k naught, that is a particular certain wave number we have to find out. So here omega square equals to alpha k plus beta k cube. So we have to find out that Vp should be equals to Vg, how much will be the k. Now d omega by dk means omega by k there should be. So you take that omega square equals to alpha k plus beta k cube, or omega equals to alpha k plus beta k cube whole to the power half. So d omega by dk will be half alpha k plus beta k cube whole to the power minus half into alpha plus 3 beta k square. So Vp equals to Vg at certain k naught. So I denote the term as alpha k naught plus beta k naught cube whole to the power half divided by k naught, that is omega by k, equals to d omega by dk, that is alpha plus 3 beta k naught square divided by 2 into alpha k naught plus beta k naught cube whole to the power half. So after calculating for simple calculations, we get k naught equals to root over alpha by beta. So this is our answer. The next question is, for a free electron gas in a metal, the magnitude of phase velocity Vp and the group velocity Vg are such that we also understand that the magnitude of the phase velocity for the free particle, we find out that Vp should be half of Vg. Now it's your homework to find it out, and please answer it in the comment section. This question, the dispersion relation for a certain wave is omega equals to root over c square k square plus m square, where omega is the angular velocity frequency, k is the wave vector, c is the velocity of the light, and m is constant. The group velocity v of the wave has the following properties. So you are given this. Sorry, I think the question is not complete. Okay, don't worry, I shall upload this question. The two options are only uploaded, the rest are cropped. Okay, don't worry, I shall upload this question. Please answer that question. And for today I think it's enough. Please, uh, happy learning. And if you find this video helpful, please subscribe the channel, also share with your friends, and thank you.